Question 1. Two men A and B supports the ends of a uniform beam 2 meter long and weighing 50 kg. A weight of 50 kg hangs from the beam from a point 0.5 meter from point A. Find the load shared by each man, assuming a bar is horizontal. Now first understand the given problem using the diagram. This diagram you have to draw. Okay. Now let us consider this is a beam of length 2 meter. Now these two fellows are holding this beam horizontally. It means that they are applying a normal reaction at this end and normal reaction at this end. Now this beam having a mass and the entire mass is supposed to be concentrated at point G. Now this point G we can also call it is a center of gravity or center of mass. So at point G the center of mass is 50 kg Wt. And this is the weight of the beam which is given here. Okay. Now C is the another point where we are hanging a 50 kg weight. Now this C is located 0.5 meter away from point A. Now this is the entire system and we are actually going to find the load shared by each man. This is the situation. Just now we discussed these two men are holding this beam horizontally. It means this beam is under mechanical equilibrium. Now what does it mean? Mechanical equilibrium means the net force on the system is equal to 0 and total torque on the system is also equal to 0. Now net force is equal to 0. That is the first point we are going to discuss. From that we are getting one equation. The next is net torque is equal to 0. And from that, we are also getting one more equation. In this way, we got two equations and we are having these two unknowns. So, two equations, two unknowns we can easily find. So, let's start with the first situation, that is the net force on the system is 0. Now, how many forces are there on the given system? Now, this is the one force which is acting downside because of the own weight of the beam, and that is at point G. So at point G, the weight of its own body is 50 kg Wt. Also, we are holding one more mass of weight 50 kg Wt at point C. So these two are the forces acting downside. And these two are the forces. The force because of the normal reaction provided by person A and the force because of the normal reaction provided by the person B. Hence, RA and RB both acting upside. And in this way, we can write RA plus RB minus 50 kg Wt minus 50 kg Wt is equal to 0. Now, how this plus sign and minus signs came into the picture, as we consider this as a positive x-axis and this as a positive y-axis. So we can have the forces along the positive y-axis are positive and the forces along the negative y-axis are negative. So these two are the forces which are acting downside and these two forces are acting upside. So they are having the corresponding directions. Now we can rewrite this equation in this format. RA plus RB is equal to 50 plus 50 kg Wt, which is 100 kg Wt. So this is our first equation that it satisfies the given condition. Total force on the system is 0. Now we will go for next, that is total torque on the system is said to be 0. Now the next condition is net torque is 0. As we know, torque is a vector, then the general formula for torque is R bar cross F bar. Now torque has a specific direction. Now in this system, we are going to apply torque on any point or any location. Why? Because whenever the system is under mechanical equilibrium, then the total torque on the system is 0 and the torque is independent on the choice of origin. Means we can select any point where the net torque on the system is said to be 0. So for a convenience, let us consider the point A where we are applying a torque. So at point A, the total torque will be, now in this case we have to write one equation based on the generalized formula, torque is R cross F. Now the forces are, this is one force, this is another force and this is one force. Now we can't take this force because at this location force is there. So the radius vector for this case is 0. So even though we can write that equation, that is AA vector. Now this is the AA vector, let us consider it is a 0 vector cross RA. Now this is a one torque. Next AC vector cross 50 kg Wt. Now this is a force, we can directly write this value here. Next is AG vector cross, now force is in downside, so let me write 50 kg Wt. Here I am writing positive signs. Let me tell you how to write signs here. So for that, let not be write here any signs. We will first write down the equation, that is the number of torques acting on the system. Now one more torque is there, that is AB vector cross RB, and that everything goes to 0. Now the question is which sign we have to assign here. Now there are 4 torques. This is torque 1, torque 2, torque 3 and torque 4. As I tell you earlier, that torque first, which is this torque, this radius vector is 0, so the entire torque goes to 0 irrespective of the direction. Now we can't get this direction because of its a 0 value. The torque is 0 itself. Now this is the second torque, that is AC, and the force is acting downside. So let me draw the diagram here. Now see this is AC vector and this is the force, that is 50 kg Wt. Now this force is acting downside. So this force vector I am simply shifting on this side and I can write in this way according to the vectors rules. So vectors are free vectors, we can shift them without changing its direction as well as magnitude. So this is one diagram that I have, so that the angle between two vectors is 90 degree. This is another vector, that is AG. So this is A and G, and the direction of force in downside. So it is 50 kg Wt. Angle between two vectors is 90 degree, and the last vector, which is AB, and in this case let me write name A into B, and in this case RB is here, so I can shift the RB so that I get a common origin here, and this is RB. Now again the angle between the two vectors is 90 degree. Now we follow this generalized formula and right hand thumb rule in order to get the direction of torque. Now according to the right hand thumb rule, this thumb is indicating this vector, then this first finger, and this is the next finger. So I will use this right hand thumb rule here. According to the right hand thumb rule, AC, that is the position vector, F is downside, so the into the plane is the direction of torque. So torque 2 is the second torque directing into the plane. As we know, torque 1 is 0 there. Now torque 3 is the AG vector, which is a position vector. Force is acting downside. So again the torque 3 is also going into the plane. Now AB is pointing in this direction, RB is pointing in upside, so that the torque will pointing outside the plane. So that torque 4 is written in this way. Now we can assume that the torque which are going into the plane are positive and the torque which are coming out from the plane are negative, and accordingly we can assign the signs. So positive sign for the torque into the plane and negative sign for the torque out from the plane. So in this way, we have this equation. Now AC is 0.5 meter. So as torque 1 is 0, I can simply write 0.5 meter into 50 kgWt plus AG is 1. See this entire AB is 2 meter, AG is 1 meter because G is the center of mass or center of gravity. So definitely it is at the origin. So AG is 1 meter into 50 kgWt. Next, AB it is 2 meter into RB we have to find, and this everything goes to 0. As 0.5 into 50, it is 25 plus 50 minus 2 times RB is equal to 0. Therefore, 75 is equal to 2 RB, and hence RB is equal to 75 upon 2, which is 37.5 kgWt. So this is the value of RB, that is the normal reaction provided by the B fellow. Now, we have to find RA by using our first equation. So from equation 1, we can write RA plus RB is 100 kgWt, and we got RB, which is 37.5 kgWt. Now RA we can easily get, which is 100 minus RB, which is 100 minus 37.5, which is equal to 62.5 kgWt. Now in this way, we got RB and RA, which is 62.5 kgWt, that is the normal reaction provided by first fellow, and RB is the 37.5, which is the normal reaction provided by second fellow. In this way, these two forces counterbalance these two forces, and the system, that is the beam, is under mechanical equilibrium and become a horizontal. This is the solution for the given problem. Next problem. A uniform bar RA's weight 100 gram and is 80 centimeter long. So this is the uniform bar having the weight of 100 gram. So weight can be located at the center of gravity, and this is the point G where the force of gravity, that is the weight of its own, is 100 gram Wt, which is acting downward. Now the entire length of the bar RS is 80 centimeter. Now from the end R, now this is the end R, two masses of 50 gram and 100 gram. So there are two masses, one is 50 gram and another is 100 gram, are hung from the bar at a distance of 10 centimeter and 60 centimeter. So this is the 10 centimeter distance and this is the 60 centimeter distance respectively. If the bar is to remain horizontal when balanced on the knife edge, finds its position. So let us consider, here we have to keep one fulcrum or a knife edge, okay, so that this entire bar is supposed to be balanced. Now the balanced means it is a condition of mechanical equilibrium. It says the net force on the system is 0 as well as the total torque on the system is 0. Now we will use the condition for mechanical equilibrium, that is net force on the system is 0 and total torque on the system is also 0. So first, according to the net force on the system is 0, we have to know first the number of forces. So this and this are the number of forces, three number of forces which are acting downside, and this is another force which is acting upside. So we can write down 50 gram Wt. Now it is negative sign because it is acting downside. We are assuming that this is a positive x-axis and this is a positive y. So downside forces are negative, we are assuming. So minus 50 gram Wt minus 100 gram Wt minus 100 gram Wt plus r is equal to 0. Now plus r because it is along positive y-axis. Now we can write r is equal to 50 plus 100 plus 100 gram Wt. In this way, the r value is 250 gram Wt. This is the equation 1. Now we will use the another condition, that is total torque. Total torque tau is 0. For that, first of all, we need to know about how many torques are acting on the system. As the system is under mechanical equilibrium, it given in the situation that is remains horizontal. So system is mechanical equilibrium. We can take any point where the total torque on the system is supposed to be 0, as it is independent of choice of origin when the system is under rotational equilibrium, or else we can say mechanical equilibrium. So here we are assuming the point which is point R, and with respect to R we will find the total torque. So that if we take RA is the position vector and this is the downside force which is 50 gram Wt, then the torque here will be produced is, let us say, torque 1. The next is Rg. So Rg is the radius vector and the force acting on point G is downside, which is 100 gram Wt. Then the torque produced because of this is torque 2. Next is R into this. Let us say this is origin O. So I will write RO, and this is the normal reaction. Now this normal reaction goes upside so that we can use this in this way. So this is also an R, so we can call this Rn. Okay, not to get confused, that this is the starting point given in the equation R. So normal reaction is now Rn. Okay, so this is Rn. Now this R is this R, and Rn is the normal reaction provided by the fulcrum. So we will call it Rn. Now in this case we are having a torque 3, and there is one more torque which is the radius vector Rb or a position vector Rb, and the force acting on point B is 100 gram Wt. Now you will surprise that I am writing this arrow at R only, not at A, not at G, not at O, even though it is actually acting at that point. This is because this is the force. This is the force, and force is a vector, as we know. It is a free vector, so we can move it without changing its direction and magnitude. So I am keeping this direction same, so that I need to find the angle between the position vector and the corresponding force, and that is comes out to be 90 in all the cases. As we know, torque is R bar cross F bar, then the magnitude of torque is Rf sin theta. In our case, it is sin 90 degree, so that the magnitude is product of position vector, magnitude of position vector, and the magnitude of force in this case. Okay, and hence, as we are having the magnitude of position vectors and forces, we can directly use this formula. So the total torque must be 0. Now these torques are vector. We will come to know about their magnitudes, but what about their directions? So for that case, we will use again the right hand thumb rule, torque, R and F. So we will use right hand thumb rule in this way. So according to right hand thumb rule, the torque 1 is moving into the plane. So I will use cross sign there. This is the same torque directed in these arrows, so it will also pointing into the plane. Now, in this case, R vector is this side, F vector is upside, so the torque will come out from the plane. And in this case, again, as per the torque 1 and torque 2, the torque 4 will be also acting into the plane. So in this way, we are assuming these torques positive and this torque negative. So accordingly, we can write torque 1 plus torque 2 plus torque 4 minus torque 3 is equal to 0. Now what is torque 1? It is Ra into 50. Then it is Rg into 100 plus Rb into 100 minus Ro into Rn, and that goes to 0. So let's substitute the value of Ra, as Ra is a 10 centimeter, so 10 into 50 plus Rg it is of 40 centimeter, so 40 into 100 plus entire Rb. Now Rb is of 60 centimeter. All these things are given in the problem. So 60 centimeter into 100, and that is equal to Rn. Actually, we got that Rn here. That is our equation 1. So let's substitute that equation Rn, equation 1, into Ro. So Ro we are interested in. Okay. Now let's multiply here. It is 500 plus 4000 plus 6000, which is equal to 250 times R. It is 10,500 upon 250, that is equal to RO. So RO is 42 centimeter. So this RO, that which is X, we are assuming here that X goes to 42 centimeter. Okay, and this is the position of a knife edge, or as we can call it as a fulcrum. So the fulcrum has to be kept at a 42 centimeter with respect to R, so that the system remains horizontal. This is the answer for the given problem. Next question. Question 3. A uniform rod has a length of 6 meter and weight 100 gram. The rod is suspended horizontally by equal lengths of two cords tied to it at a distance of 1.5 meter and 2.5 meter respectively from its midpoint. Find the tension in each cord. Now let's understand the concept by using diagram first. Now in the diagram, this is the horizontal support along with two cords having a tension T because the rod is tied. Now the length of these two cords is same, as T1 and T2 are the tensions, and this is the question that we have to find out the values of T1 and T2. Now this rod has its own weight which is acting downward side, and this is the point O where the entire mass of the rod is supposed to be concentrated. We can call it as a center of mass also. Now at point O we can show the direction of weight of the rod, which magnitude is 0.1 kgWt. Because of this, tension is created in the two cords and we have to find this value. Now we can see this, the system is stationary. Now in mechanical equilibrium, the linear acceleration and angular acceleration is 0. So the system does not show any acceleration. Now linear acceleration is 0 means total force on the system is 0, and angular acceleration means total torque on the system is 0. So we can write down first the given conditions here. So in mechanical equilibrium, total force acting on the system is 0. So we can write summation of force is 0, and total torque acting on the system is 0. It means summation of torque acting on the system is 0. Now we can write down one equation with respect to this condition and another equation with respect to this condition. So because of the total force, there are three forces actually working. This is T1, T2 and this is weight. So as we have a positive x-axis vertically upward, so we can take T1 and T2 positive. Okay. So according to Cartesian coordinate system, we can have a positive y-axis in vertically upward. So T1 and T2 both are positive, and W, which is a 0.1 kgWt, is 0 there. The sum of all these forces is 0 there. So T1 plus T2 is equal to 0.1 kgWt. This is our first equation. Now, according to the second equation, that is the total torque on the system is 0. First of all, we need to understand how many torques are actually working there. This is the rod and we can select any point on it because the system is under rotational equilibrium. The torque we can apply to any point on the system. Now that point must be lie on the system itself. Now since system, it means we are talking about rod here. So C is the point which is actually lying on the rod. So I am going to take a torques with respect to point C. So at point C there are three torques. Torques due to force T1, torque due to force T2 and torque due to weight of the rod. So let's first write down torque 1. Now torque 1 is 0. Torque 1 is 0 because according to the formula, torque is R cross F. Now in this case, if we talk about torque 1, then R1 cross F1. Now what about R1 value? Now R1 is 0 here because point C is there. So R1 is 0 and F1 is now T1 there. So in this way, we got torque 1 0. What about torque 2? So torque 2, we can write R2 cross F2. Now what is R2 there? It is CO. Now CO is the position vector. So we can take R2 as a CO into weight. Weight is 0.1. Okay. Now this is the torque 2. Now what is the direction of this torque? This is the magnitude of torque. What is the direction of it? As we have this radius vector and this is weight, we can use it in order to find direction of torque. Now according to right hand thumb rule, CO is the radius vector, so it is directed in this way. Force is directed in downside so that the torque is going into the plane. So this is the direction of torque. Now what about torque 3? Torque 3 is R3 cross F3. R3 is CD. So write down CD into force T2 which is acting upside. So this is the magnitude of torque and the direction of torque can be found in this way. See this. This is CD vector and this is T2 vector. The angle between all these vectors is 90 degrees so that the magnitude is simply the product of these two terms. Now the direction of tau 3 is again CD is pointing in this way, T2 is pointing in upward so that the torque is coming out. So this is the direction of torque. Now torque 2 is going into the plane, torque 3 is coming out from the plane. So we can take torque 2 as a positive and torque 3 as a negative. Now come to the equation again. As we have total torque is 0, it means torque 1 plus torque 2 minus torque 3 is equal to 0. As we know torque 1 is 0, so no need to worry about its sign. So 0 plus torque 2 is CO into 0.1 minus CD into T2, that is equal to 0. Now CO is given here, it is 1.5 into 0.1 minus, what is CD? It is 1.5 plus 2.5, it is 4 into T2. Now T2 we have to find using this equation as it is unknown only. So 1.5 to 0.1 is, so 1.5 to 0.1 is 0.15 minus 4 T2 is equal to 0. So 0.15 is equal to 4 T2. Hence T2 is equal to 0.15 upon 4, which is equal to 0.0375 kgWt. Now this is the T2. We are going to substitute in equation 1. We will get T1. So from equation 1, T1 plus T2 is 0.1. So T1 is equal to 0.1 minus 0.0375. And now we can write down 0.0625 kg Wt. Now in this way we can find T1 and T2. These two are the tension in each cause. This is the answer for the given problem. Next question. Question 4. From 2 points A and B in a horizontal plane, a body weighing 4 kg is suspended by two threads, one of which makes an angle of 45 degree with the vertical and other an angle of 60 degree with the vertical. Find the tensions in each thread. Now this is the diagram in which AB is the horizontal support and these two are the threads. Now we are going to hang one object having a mass of 4 kg and that will produce the tension in the two string. Now let us consider the free body diagram of this situation first. Now this body is actually having its own weight, which is, and finally addition of these two vector is one vector, which is T1 cos 45 plus T2 cos 60. Now this is one vector, this is one force acting vertically upward. Now the resolution, the T1 can be resolved. Now T1 and T2 are resolved and their horizontal components are T1 sin 45 and T2 sin 40 and T2 sin 60 respectively, so that T1 sin 45 and T2 sin 60 get balanced vertically. So that T1 sin 45 and T2 sin 60 get balanced horizontally. In this way, this body, it means it is a point we are showing here. This body is actually experiencing zero force. This force is being balanced with this. This force is being balanced with this. And hence, net force on the body is zero. It means the system is under equilibrium. Now, this equilibrium is translational equilibrium. There is no rotational equilibrium takes place. And hence, under the mechanical equilibrium, translational equilibrium takes place. So write down condition for translational equilibrium. That is, net force on the system is zero. Now using the free body diagram, we can write T1 sin 45 which is equal to T2 sin 60. As we know, sin 45 is 1 over root 2 and sin 60 is root 3 by 2. Hence, T1 can be written in terms of T2 root 3 by 2 into root 2. Now we can multiply here by root 2 and the denominator also, so that this root 2 into root 2 will get cancelled with this 2, and finally we can write T2 into root 3 by 2. So in this way we got T1 in terms of T2. We will use this step in the further calculation. Now the second equation we can write by using pair of vertical forces, that is T1 cos 45 plus T2 cos 60 is equal to 4 kg Wt. We can change this kg Wt in Newton by multiplying 4 with 9.8 meter per second, which is equal to 39.2 Newton. Now we have a T1 in terms of T2. We can replace here, but before that, let's substitute the values of cos 45, 60, everything. That is cos 45, which is 1 by root 2, plus T2 into cos 60, it is 1 by 2, which is 39.2 Newton. Now T1 is T2 into root 3 by root 2 into 1 by plus T2 into 1 by 2, which is equal to 39.2 Newton. So this root 2 into root 2 is 2 and here also one more 2. So we can take it outside. And then T2 is also there. So T2 into root 3 plus 1, which is equal to 39.2 Newton. Now, this T2 we are interested in, so that we can write 39.2 into 2 upon root 3 plus 1. As we know, root 3 is 1.73. We can substitute the value 1.73 here. Plus 1, it is 2.73. And it is 39.2 into 2. By solving this, you will get 28.71 Newton. So in this way, we got the value of T2. Now we will find the value of T1. As we have T1, which is equal to T2 into root 3 by root 2, we will substitute the value of T2 there, so that T1 is 28.71, as root 3 is 1.73 and root 2 is 1.41, and by solving this we will get 35.16 Newton. So in this way we can find out the value of T1 and T2, which are the tension in these two strings. So this is the answer for the given problem. Next question. Question 5. O is the center of an equilateral triangle ABC. F1, F2, F3 are three forces acting along the sides AB, BC and AC as shown in the figure. What should be the magnitude of F3 so that the total torque about O is 0? Now in this problem they have given the diagram, but this blue color line are not given. We have to plot it as a construction. Now what they have given is the given triangle is equilateral triangle and O is the origin of the equilateral triangle. Now the total torque acting on this point O is 0. There are actually three forces. This is F3 force acting on this side. This is F2 force acting on BC. And this is F1 force acting on AB. Now because of these three forces, the total torque acting on point O is 0. That we have to show. So let's start with a general formula for a torque. As we know, torque is a vector. Torque is R bar cross F bar. Now what is R bar here? Now X is the distance between the O and the corresponding sides, means side AB, side BC and side AC. As this is an equilateral triangle, we can consider these X are same for all cases. So X is the position vector right now. Let us say case of side AB and force F1. So because of force F1, there is a torque about point O. So let us say this is our force F1. We are drawing this diagram, vector diagram here. So force F1 is here and this is the position vector. Now this is the diagram that position vector is acting in this way. The position vector is always directed away from the origin. So this is the arrow of position vector. So we can again redraw this diagram in this way. See this? This is the position vector. We can call it as a x vector and this is F1. So now I will write F vector in this way. So without changing the direction and magnitude, I can write F1 vector in this way. Okay. Now this is my diagram for the finding the torque direction. So I need to find torque 1. As torque 1 is x bar cross F1 bar. Now angle between x and f is 90, so we can write xf sine 90. As sine 90 is 1, so the magnitude of torque 1 is xf. But what about its direction? According to right hand thumb rule, we can use x as a first finger, then f1 as a next finger, so that thumb will represent the direction of torque. So the torque is coming outside. It means we can use this symbol for the torque coming outside. So in this way, we got the direction of torque here. The same way, we have to find the direction and the magnitude of torque 2 and torque 3 due to F2 and F3 respectively. So let's draw the case of F2. Now F2 is acting in this way. This is our F2 and X is somewhat here. So X is actually acting in this way. See this? This is what the direction of X vector is. Because the origin O is somewhat here. Just like origin O was there, the origin O is somewhat here. Now we can redraw this diagram by moving F2 accordingly. So this is what the diagram is. So we can do this because the F2 is the vector, we can shift it as it is a free vector. So the angle between X and F2 is again 90 degree. Now torque 2 is X vector into cross F2 vector, that is X F2 sine 90. Again we got the same result, that is X F2 is the magnitude. But what about the direction of torque? So this is the magnitude. What about direction of torque? So in this case magnitude of torque 1 is X F1. In this case magnitude of torque 2 is X F2 and the direction is simply by using right hand thumb rule. So in this case the X is somewhat in this way, downside, and the force is coming in this way. So force is somewhat in this way. So the direction of torque is coming out from the plane. So I can write again torque 2 is directed coming out from the plane. Now for the case of F3, what will be the direction of torque? Again we will draw F3 diagram. Make sure your F3 vector will not change its direction. So this is my F3 vector and X vector is something like this. So I can write X vector is in this way. Here we got diagram correctly initially, so we can directly take this value torque 3 as X bar cross F3 bar, that is X F3 sine 90 degree. So torque 3 is equal to X F3. This is the magnitude of torque 3. Now what is the direction? It is X vector in this way, F3 is in downside, so into the plane is the direction of torque. So the torque is directed into the plane. Now we need to assume that the torques which are directed into the plane, those are positive, and the torques which are directed coming out from the plane are negative. So that according to the assumption, net torque is equal to torque 3 minus torque 1 minus torque 2. As net torque is equal to 0, we can write torque 3 is equal to torque 1 plus torque 2. As torque 3 is X F3, torque 1 is X F1 plus torque 2 is X F2. So X can cancel out throughout the equation. And finally, we have magnitude of F3 is magnitude of F1 plus magnitude of F2. So this is what the answer for the given problem.